morning. Today we'll be talking about the dynamics portion in Physics 1. Dynamics is a unit which talks about an object's motion in terms of the forces acting on it. Let's begin. For starters, let's talk about weight. An object's weight, which is not the same thing as mass is the matter that makes up the object, whereas weight is a gravitational force that Earth exerts on the object. The formula for weight is mass times the acceleration due to gravity. On Earth, the acceleration due to gravity is negative 9.8 meters per second squared. So for example, let's say we have a 10 kg ball right here, and we want to find out what is its weight on Earth. Notice how I specifically said Earth, because if I said it was on the moon, the weight will be different than that of Earth. So let's calculate. Recall that the weight force, or the gravitational force, will be the mass times the acceleration due to gravity. In this case, it'll be 10 kg multiplied by 9.8 meters per second squared. Now, I'm treating down as positive, hence I'm not putting the negative sign into my equation. Now, we get that weight equals to 98 newtons, and a newton is a kg meter per second squared. Alright, now that we're done talking about weight, let's talk about something that relates to weight. The normal force. The normal force, usually it occurs when an object's on a surface. Notice how I put this here? This means it's a force perpendicular to the object. So, for example, suppose we have an object which has a gravitational force of 10 newtons, and we were asked to find its normal force. There are two ways of going about this. For starters, you can find the mass of this object, 10 divided by 9.8, and you'll get that the mass is 1.02 kg. And just notice now that the normal force is actually just the same thing as the gravitational force in this case. So you actually didn't need to find the mass, because it's not at an angle, it's a complete 180 from the gravitational force. Therefore, they're both equal. The next force we're going to talk about is tension. Tension force exists. It's a pull force that is exerted by a rope, like material. So like a chain, a string, a rope. You get the gist. So for example, suppose we have a 5 kg ball hanging, and it's in equilibrium, meaning the net force is 0. In this case, there are two forces acting on it, the ball, the force of tension and the force of gravity. What is the force of tension? Well, recall I said that the net force was 0. Therefore, the difference between the tension force and the weight force, in this case 5 times 9.8, equals to 0 newtons, because the net force is 0. To find the tension force, you would add 49, because 5 times 9.8 is 49. You add 49 to both sides, therefore you get that the tension force is 49 newtons upwards. Now, notice how I specified direction, because force is a vector. The next force we're going to talk about is friction. Friction is a force that opposes an object's motion. There are two types of friction forces, static friction and kinetic friction. The coefficient of friction is also known as mu, and it has no units. Static mu, in this case, the coefficient for static friction will always be greater than kinetic friction, because it's harder to get an object to move than keep it in a constant velocity. So, for example, suppose we have an object that's traveling it's just moving right now, an 8 kg object, and the coefficient of static friction, or the coefficient of kinetic friction is 0.3. What is the kinetic friction force? Well, recall that our equation for friction is mu times Fn. In this case, Fn will just be the same as the gravitational force 8 times 9.8, which will give me 78.4 newtons. So we can just write down Fn equals to 78.4 newtons. Okay, now that we have that, we can just write out Fk equals to 0.3 multiplied by 78.4. Which will give us 23.5 newtons. And in this case, because I see that the object's going east, the force of friction always opposes the motion, therefore it's going west. Alright, now that we talk about all that force and those forces, what happens if there are multiple forces acting on the object? This is where free body diagrams come in. The reason we use free body diagrams in physics is to sketch out all the forces. We use it to visualize all the forces that act on an object. So for example, let's do some examples. So for starters, look at this object, a box at rest. Draw all the forces acting on it. Well, I see that if it's at rest, first off, the force of gravity is acting on this object. But not only that, because it's on a surface, there's going to be a normal force acting on it. And in this case, the normal force is just the same as the force of gravity, but that's irrelevant to this problem. Now the second one, a ball being hung by a rope. Let's see, we have the force of gravity, as always. And now we also have the tension force. And lastly, an object traveling up on a surface where friction is not negligible. So, first, the force of gravity is going down. Notice how it's not perpendicular. Gravity always goes down. It's never perpendicular to the object. And now we have a normal force, which is perpendicular to the surface here. And because I said that there was friction on the ramp, there's going to be a friction force. And the reason the friction force is going down here is because the object's going upwards. And because the object's moving, it'll be kinetic friction. Now that we talked about all the forces acting on the object, let's talk about the biggest part of this unit, Newton's 3 laws of motion. The first law, the law of inertia. It states that an object will continue moving at a constant speed, velocity, or will stay at rest until an unbalanced force acts on it. So for example, say we have a 30 kg box and we want to keep it traveling at a constant 7,500 meters per second. What is the net force needed for this object to move at this constant velocity? Well, recall Newton's first law, the law of inertia. It's already moving at constant velocity. Therefore, the acceleration will be 0. Therefore, we don't need a force, an imbalanced force, to act on this object to keep it at a constant velocity. His second law, the most famous in physics. For a mass to accelerate, there must be a force acting on it. This is the most famous equation in physics, aside from E equals mc squared. F net equals ma, or this. The sum of all the forces, which is what net force is, equals to mass times acceleration. As I stated earlier, the units for force are kg times meters divided by seconds squared, or newtons. So for example, suppose we have this 12 kg ball, and it was applied with a force of 36 newtons, like somebody shoved it with a force of 36 newtons. What is the acceleration of the ball? Well, first, we sketch out all our forces. That's what we always do in problems like these. Notice how there's an applied force, F, a normal force, Fn, and Fg, the weight. And now, Fg and Fn are equal, therefore they cancel out, and all I have is the applied force. So that is my net force. So our acceleration will be the applied force, F, divided by the object's mass, 12 kg. 36 divided by 12 gives me 3, but 3.0 newtons because of significant digits. 3.0 meters per second squared. This is not force, this is acceleration. Now let's talk about the third law, the equal but opposite forces, the action-reaction pair law. I use an equation to show what his law is, to portray his law. F sub 1 on 2 equals negative F sub 2 on 1. The negative means it goes in the opposite direction, it being the force. So for example, suppose a man shoves a wall with 104 newtons. What force does a wall exert on the person? Well, recall Newton's third law states that equal but opposite forces. If this wall will exert a force in the same but opposite direction as a person. As the person exerted a 104 Newton force on the wall is going to exert a 104 Newton force, but in the opposite direction. Now let's talk about some machines. Pulleys are the devices that change the direction of the tension force. As you can see, we have two examples of pulleys right here. So let's start with this one. Let's derive an equation for the acceleration, assuming friction is negligible. So let's look at all our forces. For starters, let's look at M1. This little dot right here that I drew. We have the normal force, Fn, force of gravity, Fg, and the tension force, Ft. Now, the normal force and the tension force will cancel out. Therefore, we get that F net, which equals to M1A. I say M1 because that's the mass of the block, which equals to the tension force. Now, let's look at the forces acting on the second mass. And keep in mind, the tensions are the same because the mass of the pulley is negligible. And yes, this is a pulley. So is this. So let's see. We have the tension force and the weight of mass 2, which we will say M2G. So the difference between tension, I'll write down here. The difference between the tension force, the difference between the weight of mass 2 and the tension force will give me the net force acting on the second mass. Now, the reason I put it in this orientation as opposed to the other way, for the other way, this will be negative because this mass has to be superior to the tension force to accelerate downwards, and we're treating downwards as positive. Now, recall that earlier we got an expression for tension force, M1A. We can substitute this in. So now we get that M2A minus M1A equals to, M2G minus M1A equals to M2A. So now we want to, like I said earlier, we want to isolate for the expression and the acceleration. Add both sides, add M1A, the net force on mass 1, to both sides. They cancel out, and now you get that the second mass, or the weight of mass 2 equals to the acceleration multiplied by the sum of mass 1 and mass 2. Now, I factored out A for a reason because you have like variables on both sides, so you can factor it out. And then now, all you do is divide by both sides. Divide both sides by M1 plus M2. As a result, we get that the acceleration in this pulley, assuming friction is negligible, equals to the weight of the second object divided by the sum of mass 1 and mass 2. Now, let's do this again, but what would happen if there were friction? Now we have an extra force acting on mass 1. The normal force and the force of gravity will still cancel out. So, the net force must equal to M1A, as we said earlier. That's nothing new. But now, instead of just tension force only, it's going to be tension force minus the friction force. And the reason tension has to be greater than friction, otherwise this pulley won't slide at all. So now let's go to mass 2. Mass 2 is still the same. The weight of mass 2 and subtract by the tension force will equal to its net force, M2A. Now we just do the same thing as last time. Find an expression for tension, which I noticed, if I move friction to the other side, I'll get that Ft equals to M1A plus FF. Therefore, I have a new expression, again. So now I get that weight of mass 2 subtracted by M1A and subtracting friction will give me the net force on the second mass. Now we do the same thing we did last time, isolate for acceleration, add m1a to both sides, and then we can factor out an a. However, one step at a time. Now we get that the weight of the second mass, and the difference between that and the friction force acting on mass 1 equals to the acceleration multiplied by its combined mass, it being the sum of the two masses in the system. Divide both sides by m1 plus m2, and those are in brackets. You will get that the acceleration now equals to the weight of the second force, the second mass, minus friction, or the difference between those two, divided by the sum of the masses in the system. Now that we got this down, let's go to our second pulley, this one. So let's see the forces acting on M1. We have tension, and we have its weight, M1G. Now, I notice that M1G is going more down and M2 is going more up. Therefore, in this scenario, M1's weight is greater than tension. So, let's write this out. M1G minus Ft will equal to M1A. And it's not negative because I'm choosing negative. One, I'm choosing down as a positive direction, and number two, M1 is superior in magnitude to tension. So, now that we have that, let's go to mass 2. We have tension, which is the same as this first tension over here, and we have the force of gravity, in this case M2G. Okay, so now let's do this. Ft minus M2G, this time it's minus equals to M2A. If I put it the other way around, it would have been negative M2A because I'm treating upwards as the negative direction. Now, let's find the acceleration for the entire system. What we can do is we don't know tension, right? And we don't want any unknown variables. So let's isolate for the tension force. In this scenario, we get that M1G, the difference between the first mass weight and its net force, is equal to the tension. And now, here, we will isolate for Ft. This time, Ft will then equal to the sum of the mass 2's net force and its weight, M2A plus M2G. So now, let's equate these with each other. M2A plus M2G equals to M1G minus M1A. So now we can isolate for the acceleration because that's what we're looking for. Like we did previously with our last pulley, let's isolate for acceleration. Add M1A to both sides so that they cancel on this side. Then, because we want acceleration all by itself, let's subtract the M2G on both sides. So now M2G will cancel out on the left side, and you get M2G on the right side. Now, like we did last time, factor out an A, and we get M2 plus A multiplied by M2 plus M1 equals to G multiplied by M1 minus M2. Notice how, since we're not looking for G, because we already know what G is, you really don't need to factor out the G. I'm just trying to make it more clear. So now, like we did before, isolate for A, let's divide both sides by M1 plus M2. Therefore, we get A equals to, the difference between the two masses' weight divided by the sum of the two masses. And that's our acceleration for this pulley. Lastly, let's talk about incline ramps. Incline ramps, or basically an object at an angle, what happens is, if you see this free body diagram here, it has components now. Usually it's not just horizontal, vertical, it's in the two-dimensional motion. We have the weight just going down, it's not perpendicular, this isn't the normal force. Then we have its parallel component. Its parallel and perpendicular component. This being perpendicular, this being parallel. Okay, now let's assume this is frictionless. How will we find the acceleration? Well, let's see. We have gravity here, but we split into its components, so we can disregard the original vector. We have mg cos theta, and then we also have the normal force right here. Now this time, the normal force can cancel out with the perpendicular component of gravity, mg cos theta. So we don't need to worry about that. Now we just have mg sine theta. That's the only force acting on it. Therefore, mg sine theta is the net force. So we can say mg sine theta equals to ma. Now, notice how the masses cancel out? So therefore, the acceleration on a ramp, assuming friction is negligible, will be g sine theta equals to a. Now, if there were friction, let's do an example with friction. Friction is mu Fn, recall that. In this case, because our Fn is mg cos theta, it'll be mu mg cos theta. Therefore, ma, our net force, equals to the parallel component of gravity, mg sine theta, minus mu, our coefficient for friction, mg cos theta. And this is assuming that the ramp is still sliding down. Basically saying that mg sine theta is greater than mu mg cosine theta. So now notice, look, the masses cancel out again. Convenient. Therefore, our acceleration for the ramp now, when friction is not negligible, will be g sine theta minus mu g times cos theta. If you want, you can factor out the g, but it's pretty futile at the moment. Alright, so now let's do one example with incline ramps. We are given two mu values, mu s and mu k, and we're trying to find out what angle will we have to position the ramp so that it doesn't slide down. Like, what's the maximum angle it can be before this box starts accelerating downwards? Well, we're trying to make it not move, right? Like, before it overcomes static friction. So we don't even need kinetic friction right here. We just need the static friction, right? Let's write down our net forces. So we see that, let's see. The parallel component of gravity, mg sine theta, has to be equal to friction, mu mg cos theta. Therefore, mg sine theta equals to mu mg cosine theta. And in this case, mu s. I should write that down to be precise. So, what can we do now? The mg's cancel out. Wonderful. Now we get that sine theta equals to mu s times cosine theta. And we're trying to find out the angle, right? Well, let's do this. Let's isolate theta for one side. Divide both sides by cosine theta. Now we get mu s equals to sine theta over cosine theta. Now, recall from my kinematics video that I covered this trigonometric identity. Mu s is equal to tangent theta. Or, sorry, in this case, because sine theta divided by cos theta is tangent theta. Now we want to isolate for theta. Easy. Tan inverse both sides. By tan inversing, taking the inverse tangent of both sides, the tangents cancel out. On the right side, tan inverse of tan theta is just theta because these two are inverses of each other. Therefore, theta equals to tan inverse of mu s. There we go. So we basically covered acceleration when friction is negligible, when it's not negligible, and how to find theta when it's static friction. If it's kinetic friction, it's not going to be the same equation. That is all we have time for, unfortunately. I hope you guys enjoyed this dynamics lecture, as I enjoyed teaching all of you. In my next video, we will be covering circular motion, when an object's traveling in a circular path. I will see you guys next time.